Hi everyone, welcome to the fourth lecture on this module 6 where we are discussing the temperature sensors. In today's class, we are going to discuss about thermocouples. A thermocouple is a temperature measurement device which is formed by joining two dissimilar metals. Okay, so when you have a metal A and metal B, both are different based on their conductivity, resistivity and other factors. Okay, when you join them together and you keep one junction at a higher temperature and another junction at lower temperature, you will find a EMF that is generated. Okay, and a thermocouple is basically based on this kind of structure. Okay, so if you see, as I have mentioned that there are two junctions, one is at low temperature and one is at higher temperature. So a thermocouple basically converts this temperature difference to a voltage. So basically it is a temperature difference measurement device. Okay, and this thermocouple is categorized under thermoelectric devices. Okay, so what is a thermoelectric device? A thermoelectric device is a kind of device that uses the thermoelectric effect to convert the temperature difference into electrical energy or vice versa. So anything electrical energy can also be converted into the temperature difference, or both are actually thermoelectric phenomena. Okay, therefore these thermocouples are also known as thermoelectric thermometers. Okay, the use of thermocouple is based on thermoelectric phenomena, as I have mentioned, and this was a discovery by Thomas Seebeck in 1821. Okay, voltage is developed when two metals are connected together at again two different junctions. So I have a metal A and metal B, they are joined together at two distinct points, say X and Y. Okay, and the temperature at X is say T1 and Y it is T2, and T2 is say for example greater than T1, you will find a EMF generated. Okay, this voltage is a function of the temperature of the junctions and the difference in the temperature. Okay, the electrical conductive material exhibit basically three different type of thermoelectric phenomena. The first is the Seebeck effect, second is the Thomson effect, and then we have a Peltier effect. Okay, so three different thermoelectric phenomena can happen. One is Seebeck effect, then Peltier effect and Thomson effect. Okay, let us try to understand these three different effects in very brief. Okay, Seebeck effect is when there is a temperature difference across a thermoelectric material, it generates a voltage. So when there is a temperature difference across these two junctions, there will be a voltage generated. Okay, the Peltier effect suggests that when an electric current passes through the junction of the two different materials, it can absorb or release heat. So you can understand this Peltier effect as just opposite to the Seebeck effect. Okay, what is happening in the Seebeck effect? You are giving a temperature difference at the two junctions. Okay, and in what you are getting is basically a voltage. So you are creating a temperature difference and you are getting, what you are getting is a voltage. Okay, in case of Peltier effect, in the same kind of junctions, okay, what you are giving is you are providing a current. Okay, and when you are flowing this current in this junction of two different material, what you are getting is a heat generated or sometimes heat absorbed. Okay, this is the Peltier effect. Then there is one more effect which is known as Thomson effect. It describes heat absorption or emission within a single material when current flow through a temperature gradient. So I am talking about the same material, say metal A, I have a temperature gradient. Okay, when current is flowing through it and there is a temperature gradient, you have a heat absorption or emission in the process. Okay, so three different thermoelectric phenomena are Seebeck effect, Peltier effect and Thomson effect. Okay, we will be taking help of the Seebeck effect at least in this thermocouple module. Okay, a thermoelectric contact transducer is called basically a thermocouple because at least two dissimilar conductors are joined to form a junction or a couple. Okay, because this as you are forming this device by taking a couple of metals, okay, it derived its name from that. Okay, that's why my name is thermocouple. Okay, so it's a thermoelectric device and using a couple of metal wires, right? That's why I'm calling it a thermocouple device. So at least two of these junctions are needed to make a practical thermocouple sensor. It generates voltage in response to temperature and does not require any external excitation power. So you do not give any external biasing to this thermocouple and it generates voltage in response to the temperature gradient. Okay. As the thermocouple is a voltage generating sensor, it converts thermal energy into electrical energy, right? So this is the thermoelectric device which is converting this thermal energy. This thermal energy is generated by the difference in the temperature that I have just mentioned, okay, and this energy is converted into voltage, which is a form of electrical signal. Agree? Then because of this, I can also call a thermocouple as a thermal battery. Okay, it's a source of voltage because of temperature gradient, or because of this thermal energy I am getting a voltage. Okay, that's why this device is also known as thermal battery. All right, but let us try to understand the EMF relationship for a thermocouple. Now consider two different materials, metal A and metal B. Now usually in the thermocouple, one junction which is common is known as hot junction. Okay, this junction is known as hot junction. Sometimes it is also called sensing node or sensing junction. All right. So a thermocouple has a common junction and then two different terminals are there. I have attached voltmeter here. Okay. So my device looks something like this. I have a common node and two different nodes through which I have connected a voltmeter, and this all is happening in two different material A or metal A basically and metal B. The Seebeck effect used to measure temperature requires a combination of two wires with dissimilar Seebeck coefficients. Okay, we'll come back to Seebeck coefficient, but for the time being you understand that material A and material B is entirely different. Okay, and they have dissimilar Seebeck coefficient. We will define Seebeck coefficient in some time. The name thermocouple reflects that wires with two different composition are combined to form a thermocouple circuit. We have discussed this some time back. Okay. Now in this circuit, I am calling this a thermoelectric circuit. Okay. If we can have a equation sigma is equal to del E by del T. Okay, where sigma is the thermoelectric power and is also known as Seebeck coefficient. Okay, and sigma is a function of temperature. So sigma is defined as del E by del T, where del E is the change in the electromotive force and del T is the change in temperature or the temperature gradient. So I can simply write del E as equal to sigma into del T, right? Del E is equal to sigma into del T. Okay. The EMF generated in material A between the junction this temperature Tt and Tj, okay, EMF can be written as integration of this sigma into dt from temperature Tt to Tj. Okay, this is the EMF generated in material A between the junction temperature Tt and Tj. Okay, I am calling it EATJ. Okay, so this EMF generated is equal to sigma into dt. I am using a subscript of A to denote the Seebeck coefficient sigma for material A. Okay, so E is equal to integration of sigma from temperature Tt to Tj, right. Now, applying this equation to the consecutive segment of the circuit, what I will get is EAB is equal to Tt to Tj of sigma A into dt plus Tj to Tt of sigma B into dt. Okay. So, basically the summation of two energies sigma A into dt for material A and while going from Tt to Tj, please note that direction is very important in the thermoelectric devices. Okay. So, Tt to Tj, from going from Tt to Tj, integration for material A, this part is for metal A and this is for metal B. Please note this temperatures. For metal B, I am going from Tj to Tt. Okay. So, EAB is equal to Tt to Tj sigma A into dt, and for sigma B you have Tj to Tt sigma B into dt, where sigma A and sigma B are the absolute Seebeck coefficient of metal A and B respectively. Okay. This is the EMF equation. The order of integration is specified by moving continuously around the loop from the terminal to the junction and back to the terminal. This is very important while considering any thermocouple circuit. Okay. The position of the junction around the thermocouple circuit is identified by the x coordinate. Please note this x coordinate. Okay. It suggests the direction. For the purpose of analyzing thermocouple circuit, the physical length of the wire is actually immaterial. Okay. So, it does not matter actually. Okay. Accordingly, x should be thought of an indicator of positions only, since I am not considering the length and it is basically not the measure of distance. Okay. It is just indicator of the position. Okay. Notice that the value of EAB in this equation is due to integrals along the length of the thermocouple element, right. This leads to an essential and often misunderstood fact of the thermocouple thermometer. The thermocouple junction perform two different roles here. The junction provide electrical continuity between the two wires of the thermocouple. So, when this is the junction I am talking about and these are the terminals. Okay. So, the junction provide electrical continuity between the wire A and wire B of this thermocouple. Okay. This junction also provide a heat conduction path that helps to maintain the end of two dissimilar wires at the same temperature Tj, right. You have seen this already, right. So, the role of junction in thermoelectricity are two. First is the junction provides electrical continuity between the wire A and wire B of this thermocouple. The junction also provide a heat conduction path that helps to maintain the ends of two dissimilar wires at the same temperature Tj. Alright. That is why I called it a sensor node also, or sensor junction also. Alright. The EMF of the thermocouple exists because there is a temperature difference between the junction at Tj and the open circuit measuring terminal at Tt. Okay. Now, we have seen that EAB is equal to sigma Tt to Tj sigma A T dt plus Tj to Tt sigma B into dt. This was my equation for EAB. Now what I will do is I will switch the order of the limits of the second integral. Okay. If I do that, my new equation will be, what I have done is I have reversed this order. So what I am trying to do is I am trying to bring both the limits like dt to tj. Right now the second integral is from tj to tt. Okay. So I am trying to write this equation, okay, keeping everything constant. I am not touching anything else. Okay. What will happen is I will just write a negative sign, or I have to put a negative sign because I am reversing the integral. Okay. So now this EAB will be equal to tt into tj sigma a into dt minus tt to tj sigma b into dt. Please note that this minus sign is very important, and it also emphasizes the role of the direction, and that's why you have seen that we have used a notation x to provide the direction of the flow. Okay. So now I have integration from tt to tj in both the terms for metal A as well as for metal B. Okay. So EAB can be written as tt to tj sigma A minus sigma B into dt. Of course, sigma A and sigma B are the functions of temperature. Okay. So EAB will be equal to tt to tj sigma A as a function of T minus sigma B is also a function of T into dt. Fine. Now I will define Seebeck coefficient of the material pair AB. Now I have two metals. I was using metal A and metal B to make this thermocouple. Now I have defined a Seebeck coefficient. I know absolute Seebeck coefficient for metal A is sigma A, for metal B it was sigma B. Now I will define Seebeck coefficient of the pair AB. Okay. So sigma AB can be written as sigma A minus sigma B. Okay, where sigma AB is also a function of temperature, and sigma A and sigma B individually they are also a function of temperature. So EAB can be written as TT to TJ sigma AB into dt, right. So this is the equation of the potential. All right. So if the two materials have the same absolute Seebeck coefficient, so now consider that if for material A and material B, sigma A and sigma B are equal, okay, in that case the thermocouple generates no EMF, okay, regardless of the temperature difference. So whatever will be the temperature difference TT to TJ, okay, regardless of this, if this sigma A and sigma B for both the material are same, there will be no EMF generated. Okay. So usually what you want is you want sigma A and sigma B to be as apart as possible, right. So whatever will be the temperature difference, as high as you create, there will be no EMF. Okay. There are a standard combination of materials that provide large values of sigma AB that are slowly varying with T. Okay. Now you have this equation of sigma AB and EAB. If you substitute this, you have got EAB as equal to sigma AB into dt, as we have discussed. Again, integral from TT to TJ means the open terminal temperature to the temperature of the junction. Okay. So this equation is the fundamental equation for the analysis of thermocouple circuit. This is very crucial for analyzing a thermocouple circuit. Please note that this equation is still not in the form of computational formula for data reduction. Okay. So indeed the conversion of thermocouple EMF to temperature actually does not require the evaluation of integrals. Okay. So before a data reduction formula can be developed, the roles of the junction has to be identified, and we have identified it to certain extent. Okay. So this is a thermocouple, just an example of a thermocouple. You have a constant and iron wires, then different leads, and then thermocouple control junction box, copper lead, and then you have some voltmeter or something to measure the output. Okay. The EMF developed in this thermocouple circuit can be given as E is equal to A into del theta plus B into del theta square, where del theta is the temperature difference between the hot thermocouple and the reference junctions, and A and B are the constants. This formula is basically used for calculating the thermocouple EMFs. Okay. Usually A is larger as compared to B, and the EMF of thermocouple it can be sometime simplified as E is equal to A into del theta, where del theta is of course E by A. Okay, and A, as I have mentioned, is a constant. Okay. So the thermoelectric EMF depends on the temperature difference between the hot junction and the reference junction or the open circuit temperature. Okay. Any change in the reference junction temperature can affect the difference and introduce measurement errors. Okay. So in this equation, if you see, if I consider E is equal to A into del theta or A into T2 minus T1, okay, so this is junction temperature, this is the reference junction temperature. Okay. So if you have any change or any disruption in this temperature T1, for example, okay, this will result in measurement errors and you may end up getting erroneous results. Okay. Therefore, the reference junction should be kept at a constant temperature for all the thermocouples for a better calibration. Okay. So temperature maintaining of this reference junction is very important. The temperature of reference junction is therefore controlled. Okay. So the reference junction temperature is usually 0 degrees Celsius, but depending on your scenario you can change it. Okay. So just have a look on different combination of different metals, okay, and their EMF generated versus temperature curve. Okay. This is a chromel and constantan data, this G1. Okay. Then you have this iron and constantan data. So this strong line suggests a continuous reading, while this dotted line is a spot reading only. Okay. So this is chrome and alumina, then copper and constantan. Okay. Then tungsten, rhenium and tungsten again, of course it was 5% and 26%. Okay. This is C. Platinum, 10% rhodium and rhenium. This is one of the important thermocouple combination. Then you have rhodium iridium kind of thermocouples, and this is the EMF versus temperature data. All right. So there are I mean, depending on material and their combination, different types of thermocouples has been proposed, and their names are from by alphabets like B, E, J. Okay. So type B thermocouples are nothing but platinum 30% rhodium and platinum 6% rhodium. Okay. And their temperature ranges are around 1370 to 1700. Okay. Then type E thermocouples are nickel chromium and constantan combination. Okay. And usually its temperature range is from 0 to 870 degrees Celsius. Type J, which is very popular, okay, is iron and constantan combination, and it is used in between 0 to 760 degrees Celsius. Okay. Then type K thermocouple is a nickel chromium and nickel aluminum combination, which can have a range from 0 degree Celsius to 1260 degrees Celsius. Okay. Type N thermocouple is nicrosyl and nisyl combination. It is again from 0 to 1260. Okay. type R is a platinum 13% rhodium and platinum combination, and it is usually useful at the higher temperature range, usually from 870 degrees Celsius to 1450 degrees Celsius. And apart from this type R, there is one more thermocouple, which is type S, which is again used for high temperature measurement, and that is a combination of platinum 10% rhodium and platinum, okay, very similar to type R, okay, and its temperature range is around from 980 to 1450. And then you have a type T, which is a combination of copper and constantan, and it can be used in the negative temperature range also, so minus 59 to 370 degrees Celsius, okay. So these are different thermocouple types, and this types is easily, I mean, mostly adopted by the industry, okay. So they go by this name. So every time they will not call that a combination, they want a combination or of iron and constantan, they will simply say that, okay, oh, type J thermocouple. Similarly, they will not call nickel chromium, nickel aluminum kind of combination, they will simply call thermocouple type K, okay. That's why these nomenclatures are very crucial in case of thermocouple, okay. Then there are certain limitations of these thermocouples, particularly the low voltage signals that is generated in the process of this this measurement, okay. Therefore they are very susceptible to external noise, okay. Therefore, I mean, you have to be very careful while measuring the voltages that is generated by these thermocouples, okay. Then the material compatibility at high temperature is another issue, because you have seen that you are using this at very high temperature, okay. So their compatibility at high temperature is very essential, and because of that this temperature thing, long term stability of this thermocouple is also very challenging, okay. So so there are certain limitations of this thermocouples, but then they are very useful devices, okay. They are not only useful when they are used individually, but they are also very essential when you use it in a combination of in combination with other thermocouples, okay. So usually they are used in series combination, and a number of thermocouples connected in series are known as thermopiles, okay. So a thermopile is a device which convert again a thermal energy into electrical energy, and it consists of several thermocouples connected mostly in series, but sometimes they can also be connected in parallel, okay. And this is a typical thermopile structure where these connections shows different thermocouples in series, okay. So the purpose of thermopile is to measure temperature difference, again very similar to the thermocouple, because it is nothing but a series combination of thermocouples, okay. So this temperature difference is proportional to a heat flux flowing through the thermopile and the material which is embedded, okay. And this del V is equal to N into sigma A minus sigma B into del T, where N is the number of thermocouples which are connected in series, and sigma N and sigma B carries the same meaning that it carried in the thermocouple, okay. So thermopiles are the devices which are heavily dependent on thermocouple, and since the sensitivity of thermocouples are not very high, they are almost always connected into series, and when they are connected in series, they makes this kind of thermopiles, okay. So this is all about thermocouples and thermopiles. They are very efficient thermoelectric devices, and you know, several device structures has been proposed based on this principle, okay, and using a combination of different metals. But as I have mentioned that these conductor combinations are mostly very popular, particularly because the practical value, I mean practical sense of sigma AB is available, okay. So I mean, when I say practical sense is possible, means that sigma AB is large enough to be read, large enough to be applied in a thermoelectric circuits, alright. So with this, we finish this thermocouple and thermopile section. In the next class, we will discuss some other temperature sensor. Thank you.